Hi guys, my name is Matheus Farias and I'm a member of the IoT. That is our system. And basically, it tries to identify some impulsive sound he was trained and locate these sounds from the difference of how long it takes to reach each microphone. If a desired sound is identified by the system, the coordinates of the sound source are calculated and sent via Bluetooth to a mobile phone. The project was initially motivated by a recent survey by Correio Brasiliense, titled Brazil Leads the Ranking of Firearm Deaths in the World. Based on this strong data, the idea of locating shooters is quite relevant for public safety worldwide. It's also possible to see several examples of alarming news about firearm use in other countries, such as nearly 40,000 people died from guns in US last year, highest in 50 years. Given this, the proposed project has as its application focus the allied use of location technology in conjunction with police performance. The system can be applied statically as fixed to posts or buildings, as well as coupled to police cars, which can be alarmed live during the rounds. Therefore, the great user of IoT would be the government itself as a measure of improving national public security, despite the great benefit it is to the population.
Our system can be divided into two parts. The first part is the simultaneous acquisition and storage of microphone data. Data is acquired from a preamplifier circuit for the microphones, which is connected to the FPGA ADC inputs. In FPGA, data from all microphones is stored in a circular memory type, which stores in real time the last half second that each microphone collected. Still in the FPGA, there is a threshold, which will analyze the intensity of the samples of a microphone, and if it has a number of samples above the threshold, the system stops and we go to the second part, the data processing and communication. When the threshold is exceeded, the microphone data is loaded into the hardware processor system and goes through a pre-trained artificial neural network that identifies some kind of impulsive sound. If the sound is actually identified as a desired sound, the time taken for the impulsive sound to arrive between the microphones is calculated using correlation methods, and then a multi-iteration algorithm is used to estimate the sound's location. After this information is sent via Bluetooth to a mobile phone.
To make the system work, you first need to connect the microphone in a circuit that amplifies the audio signal before sending it to the FPGA. Then, you must save the generated SAW file in Quartos and run the project executable in the hard processor system. Finally, we connect the mobile phone to the Bluetooth module connected to the FPGA. This program has been trained to recognize and locate claps a few meters away. Let's do some simple demos to illustrate how the system works.
So this is the x-axis, the y-axis and the z-axis. The first test will be done in x equals 3 meters, y equals 0 meters, and z equals approximately 1.5 meters. Now I will turn on the Bluetooth. Connecting. Connected. Okay. Now the test. Okay. Test number 2. X equals 5 meters, y equals 0, z equals approximately 1.5 meters. Put the Bluetooth, and now the test. Okay. Test 3. X equals 5 meters, y equals 2.2 meters, and z equals approximately 1.5 meters. Turn on the Bluetooth. Connect. Okay. So now the system was trained to only recognize some types of fireworks. We will do the tests in x equals -7 meters and y equals 0. First I will connect the Bluetooth. Connected, okay. First, the test will be done with an airsoft gun. Okay, now with claps. Again. Okay, now the firework. Okay. Okay. Now the test will be done with a firework in x equals -16 meters and y equals 0. First I will turn the Bluetooth. Connecting. Connected. Okay. Now the test. Okay.